So I'm going to talk about optimizing crop yield forecast with red edge bands and deep learning. So I will start with discussing the vegetation indices, especially the NDVI, and highlight its limitation in crop yield prediction and forecasting. And then I'll move to present red edge spectral bands and demonstrate their potential in improving crop yield models. And then I'll finish up with a case study on deep learning or crop yield prediction and forecasting. So I'm pretty sure like most of you guys, you worked with the NDVI and you know what it is, but I'm just gonna go through it again just in case. So NDVI is usually used as indicator for vegetation vigor and health. And in most of the studies, they use the NDVI to correlate with the chlorophyll content, biomass, yield, and leaf area index, and some other traits. And in other studies, they use the NDVI to detect nutrient deficiency, for example, and the disease also detection. And as you can see here in this figure on the top, when plants are healthy, you can see a higher NDVI value, but for stressed plants, you'll see very low NDVI values. And as you can see here from the equation that it relies on red and near infrared bands. But unfortunately, as you know, that it ignores the red edge region. So if you see here in this figure, so the red edge region is not really used by the NDVI, but this one is really really sensitive to subtle changes in plant physiology. So we wanted to know a lot more about the NDVI and how it is used for crop yield prediction, and we wanted to see if it's really useful. And we did a systematic review and meta-analysis on the NDVI. So our research focused on some keywords, yield, wheat, and NDVI. And we focused on the period from 1990 until 2024. And we have screened about 1,028 sources, including articles, journal articles, presentations, and other sources. And we filtered all the data, and we got only 41 studies for the meta-analysis. And this is because these studies, they provide the yield data and NDVI data as CSV files or the plots. So in case they don't provide them as CSV files, they provide them as plots. We just use something called Web Digitizer to extract the information from these plots. And then we made some plots to assess the relationship between NDVI and yield. I'm not gonna go through all the information, but you can read this paper, which was published just last week. And I'm going to show you just some of the results from this review. So as you can see, they still use NDVI as a predictor for crop yield over time. So you see this increasing number of publications. And you can see that the R squared is really higher in the northern regions of the world. Maybe this because of better climate conditions or soil conditions. But I'm really interested in this plot in here, in the scatter plot, because it shows you really clearly the NDVI issues, the saturation issue. So as you can see, over 0.75, the NDVI start to saturate. So it doesn't really matter, like if you have 0.2 tons per hectare or 12 tons per hectare, you will have almost the same NDVI. So you see this vertical line. So you can see the saturation issue very clearly. So it doesn't really matter the study scale or the NDVI measurements or satellite or growth stage. So if you use the max NDVI or minimum or whatever you get at this point, you'll get saturated. And then what we've done, we plotted the NDVI against yield at different scales. Local scale in here, I don't know if you can see it, and regional scale, and then global scale Yep. At the local scale, the relationship is almost linear. The saturation issue or like the climate dependency is not really clear, but as you go at regional global scale, so you see like more residuals. And from the box plot, you'll see at the global scale is the highest residuals. And this is because NDVI, as you know, it's dependent on the climate. So the key points from this study, from the meta-analysis, that the NDVI will saturate above 0.75, and which this causes the underestimation of yield. And the relationship is nonlinear between NDVI and yield. And the reported studies oversimplify the story, unfortunately. And the relationship between NDVI and yield, they affected by study scale, sorry, and the difference in management practices and climate. So now I showed you some issues with the NDVI saturation issue and the dependence on climate as well. So what's the alternative? So we have here two questions. How does the integrating of the NDVI of the red edge bands affect the accuracy of crop models compared to the NDVI or other traditional vegetation indices? And to what extent the red edge based indices reduce the nonlinear bias across different climates or different regions? We've done a study. This was published this year as well. So the study aimed to develop a new vegetation index that uses three red edge bands provided by Sentinel-2. And we evaluated the performance of this index by comparing against some of the vegetation indices that use 0, 1, 2, and 3 red edge bands. So what we've done, we take every vegetation index and we feed it to the simple model. I'll show you in a second. And then after that, we make the correlation plots, and then we see which NDVI, which vegetation index lets the model get the highest quality. And we used about 168 canola fields and 123 wheat fields from different regions across Australia. As you can see here, they come from different regions and climates. And this is just the number of the fields we use. You see, they come from different years. And these are the indices we've used. So as you can see here, the NDVI does not really use any red edge bands. You know that. But for the VREI, it uses 1. For the CIR, it uses 2. For the 3MSRE, it uses 3. And the TREI, which we proposed, it uses 3 as well. The way we formulated the TREI index, we just tried to capture the changes in chlorophyll content. And we found in the literature this is the best thing to do by subtracting red edge 1 from 2. And to capture the variation in plant structure and the canopy structure, we found this the best equation. We got the reflectance from just from one field as an example from the study area. So as you can see here, that the reflectance obtained from Sentinel-2 for the red edge 3 and 2, they have higher values for the high production areas or healthy, you can say healthy plants. But for the low production area, you see that the red edge 3 is low. And clearly this batch has some issues because it has also low yield. So the reflectance in the red edge 2 and 3, they are lower. But the red edge 1 reflectance, you'll see higher in the low production areas. So this is the simple model I just talked about. So it's simple model. So in this model, we just say that more radiance, more sun, more rainfall, you will get more energy conversion. You convert to biomass and then yield. And then we feed the energy conversion to this model where we multiply the vegetation index, each vegetation index we multiply it by EC, and we tune it with a parameter called A. I'll also explain this parameter in a second. But then we got two data sets, one for the calibration and another for testing. So the one for calibration was taken from site 1 and 4. And we divided this set 60 and 40 for training and validation and until we get the minimum RMSC, and then we just test on the sites 3, 2, 3, and 5. So here you go. We got some results. As you can see here, the NDVI values are saturated very quickly at 0.71 in this field. So it's really clearly, you can see that the NDVI has issues. And from this histogram, you'll see that all saturated had high values. But the other indices, the VRA, CIR, or whatever, they don't really saturate as the NDVI. And I just want to show you the scatter plot as well. You see again, here the NDVI saturate for wheat and canola, but the other indices, they don't show saturation as the NDVI. And regarding the model's performance using different vegetation indices, you can see clearly that the TREI outperformed the other indices. The NDVI, again, it has some issues with the saturation. You'll see that there is like horizontal line in here. And I think like it's not really reliable to use the NDVI in the model. So it's not going to give you good estimation of yield. And I just want to show you this table very quickly. This like again shows you that TREI outperformed the other indices based on year and crop type as well. And here is the parameter A values. So we tuned based on the rainfall bins. So we decided 50 millimeter of bins. You can see that for the TREI, the tuning is less because you'll have from 150 until 220 millimeters, you will have the same parameter or factor, but you'll see for NDVI, you'll have different, for example. And again, for the CIRs, it's good, it's similar to the TREI, but once you go to higher bins, you'll have quite different parameter values. So the TREI is really stable more than the others indices. So the key points from this study, so the TREI outperformed the other indices. It seems that using the 3 red edge bands from Sentinel-2 is really preferable to get better estimation of yield and biomass or other traits. And the red edge based indices, they can perform better across regions. So it doesn't really depend on a lot, same as the NDVI on the climate. So after I showed you the limitations of the NDVI, and I showed you there is a potential using the red edge bands, I want to show you some satellites that can provide the red edge bands. So now we are writing another review. We're trying to see how many satellites they provide this bands and what's the wavelengths of each red edge bands. And we found that publications that use the red edge bands has increased since 2010. And nowadays, more than 15 platforms, they can provide red edge sensing, either multispectral or hyperspectral. And we can see that commercial satellites such as WorldView and PlanetScope, they can provide the red edge at higher spatial resolution. And with the hyperspectral platforms such as Chime, or if I can pronounce it right, Chime, I think. So they can give red edge bands at very, very high spectral resolution, because they are hyperspectral. And here are some other information. So you can see the good news that, for example, Landsat, they're gonna launch it in 2030. They're gonna provide some red edge bands. And the good thing is they are almost similar to the red edge bands 5 and 6 in Sentinel. So they have almost similar spectral range, which is really good because both they are like they come at high revisit time. So for Landsat, I think it's 6 days, and for Sentinel-2 is 5 days. So imagine if you can get image today, and after 3 days you'll get from Landsat another image, so you will have high revisit time. But most of the satellites anyway, they have high revisit time, as you can see here, less than 5 days, most of them. But I'm really interested in Rapid Eye and Sentinel-2 because I got some access to some of the data from Rapid Eye. And I just want to show you two images here as an example. So I got two images, one of them from Rapid Eye in 2019, July 18th. It was taken 9 o'clock, around 9:42. And the other one, Sentinel-2, it was one day earlier, or 22 hours earlier. And you can see that the spatial resolution is different. And there was no clouds. And the off-nadir angle is different as well. It's slightly different for both. And the view azimuth not provided, unfortunately, by Rapid Eye, but it's around 286 degrees for Sentinel. And the sun azimuth is not really that different. For the sun elevation also is not that really different. But when you look at the Rapid Eye NAR and red edge bands, you'll see that they are slightly higher compared to the Sentinel-2. So the VREI, you will get much less than the Sentinel-2 VREI. And this is because of the spectral resolution and also might be because of the azimuth angle, which changes the illumination of the target. And here you can see the highest you can get from Rapid Eye VREI, you'll get like 2 point something. And for the Sentinel-2, 3.6 or 7. So imagine if you feed this VREI to the model that I showed you. So you'll get different yield estimation using both sources. It is another example. I said like maybe because they are different satellites. So I got two images from different times, but for the same satellite. So you can see the correlation is not really strong. It looks like a nice fish anyway, the correlation. But when I looked at the metadata, I saw they come from, same satellite, same instrument, same spatial resolution, almost same off-nadir angle, but the most important thing, the sun azimuth and sun elevation different as well. Maybe this causing this variation, even if the difference is just like less than 1 day. So there is a significant difference in the correlation. Unfortunately, I tried to find another image that provide red edge, but I couldn't. Then I got these images, three images so two from PlanetScope, image 2 and 3, and image 1 was taken from PlanetScope derived from SkySat. So you see the correlation between 2 and 3 is high, but 2 and 1 lower than the 2 and 3. And also I got some metadata in here, so you can see the difference between image 1 and 2 and 3. You'll see that this was taken the 1st of September 19, but this one second and this also second. So on the difference between image 3 and 2 and 3, you'll see only 5 minutes. But the view azimuth is significantly different, but not the sun azimuth and the sun elevation. So the key points from this, So you can see that the red edge bands becoming more available at higher spatial, spectral, and temporal resolutions. And different satellite models, they have different sensor calibration. So the output should be different because the different specifications, even the dates are the same. So you have to be cautious when comparing different vegetation disease from different satellites, even if they are the same date. So I read something in the literature, they say the best thing to do applying the BRDF correction. So you look at the target from the same angle, especially when you work in with the time series. So after I showed you the importance of the red edge and the limitations of the NDVI, I just want to show you very quickly the case study on deep learning. So as you know that deep learning is increasingly used for crop yield forecasting because they can model complex and nonlinear relationships between different factors and the target, such as yield. And they can accept structured and unstructured data. What I mean by unstructured data, they are like the structured data which are organized as rows and columns, while unstructured, they basically satellite images or rasters in general. And models such as CNNs, they can handle unstructured data, while the DNNs, they can handle the structured data. This will be presented next month in Spain, so I can forward a draft of this paper. So the case study we've done, we aim to forecast yield at within field scale using limited but representative data, and each field was modeled individually. For example, field one, we took like 16 and 19 for training and validation, and we used 23 for testing. And we use TabNet, fully connected layers, 3D CNN, and XGBoost. So the reason we selected TabNet, for example, is because the authors claim that it outperformed all the models, the traditional machine learning models such as XGBoost. And of course, like the fully connected layers, they are the baseline for the deep learning model. So that's why we selected it. And the 3D CNN, because they can handle the images or rasters. And we use some variables such as elevation EM50, gamma, thorium, and the evapotranspiration from May to August. So this is because we wanted to forecast yield. That's why we had to take the images from May to August, which is the mid-season. And we followed the leave one season out cross-validation approach. And we used Triple C and RMSC for evaluation. So I just want to show you very quickly the architecture of each model. As you can see here, we used the fully connected layers, as I said, as one dimension. We have two fully connected layers with 256 and 128 neurons for each layer. And we have two dropout layers to prevent overfitting, and we use the ReLU function. And for the XGBoost, it's a really simple model, as you know. It's basically the sequential learning. It's not like random forest. You take the average of all trees, but you just each tree will learn from the previous tree. So that's the difference between the XGBoost and random forest. So we use this model as well. And here's the architecture of the CNN model. So we use 3D stack. We stacked all the layers together, and until we get the forecasted yield maps. So we use two CNN layers with 36, 36, and 24 filters, and kernel size of 3 by 3 by 3. And the activation was leaky ReLU. And the batch normalization was also used after each 3D cone layer. And we used two max pooling layers, and the flatten layer also was used to convert the 3D to 1D. And we used two fully connected layers after that, and also dropout layers to prevent overfitting. And then with the final thing we have done, we just reshaped the data again to rasters. And we used the optimizer called Adam, and we used two loss function called MSC and MAE. We use also a tablet, as I mentioned as well. And the tablets, it has many functions, but I just want to show you very quickly what each decision step is. So you have decision steps consisted of feature, transformer, attentive transformer, and mask functions. So the feature transformer, it processes all the features, the raw features or selected features to make new patterns and to capture the interactions between features and just reduce the noise. This is just to provide the model with better representation for the predictions. And you have the attentive transformer after each feature transformer. This is used to mask or gate the input features to the following step. And then we have a mask function in here. Maybe I can zoom. So the mask function in here, it will just tell the next step that these useful features that the model should use. And also it gives you some information about the feature attributes. It's similar to the global and local feature importance in traditional machine learning. The final predictions are made by aggregating all the decision outputs from all steps. So in our case, we use 5 decision steps to make the predictions. So if you're wondering if we tuned the models, yes, we tuned all the models we mentioned. So here are some results. So as you can see in the box plots, that in 2016, for example, in field 1, you will have higher yield compared to the 19 and 23. So the reason I think we're thinking that because of the ET is almost similar in July and August, and you can see here there's massive difference between these in July and August for both years. And if you look at this year and here as well, you will have almost the same. And for 2020, almost the same as well. But here you can see that much lower ET in July compared to August, so you have less yield. And regarding the performance of the models, you can see the 3CNN achieved higher triple C in fields 2, 3, and 4, and lower RMSC in field 3 and 4. And this is because the 3D CNN can capture the spatial interaction, spatial in field 3. I'll show you in a second now why. And the XGBoost, it's not like the authors claim that the tablet can, for example, outperform the XGBoost. So it could not really outperform in our study. Also, the tablet and fully connected layers were inconsistent, so they are not really reliable. And I just want to show you the patterns that I talked about in field 3. So you can see that over the years, the patterns are almost the same. And that's why the 3D CNN outperform the other models. So when the patterns exist over time, so the CNN works very well compared to the other models. So the key points from this study, the 3D CNN most effective way for yield forecast when patterns are consistent across years or seasons. And XGBoost is still better than the tabnet and the fully connected layers. And actually, we need to integrate more variables to improve our models. I think that we need to think about data representativeness over the volume. So if you have like large volume of data, but the patterns are not really exist, then it's just garbage in, garbage out. So the key takeaway, so the red edge-based indices outperform traditional vegetation indices as I showed. And you have to be cautious when comparing vegetation indices across different scales, dates, and sensors and viewing angles. Deep learning outperform the other machine learnings when patterns are exist. So yeah, so this is like my presentation today. Thank you.